In 10D, we have a rational inequality, and it's extremely important that we don't multiply through by the LCD. So this LCD technique we do for equations is off limits. Do not do that. What you want to do, and our strategy was to get one side equal to 0. So I'm going to leave the x minus 3x plus 4 on the left. I'm going to subtract the 3. It's greater than 0. And then we said we're going to rewrite it as a singular rational expression. So this is over 1. So I want to make sure I use my common denominator to rewrite it as a singular rational expression. So my common denominator in the only denominator that I have is an x plus 4, so I'm going to multiply top and bottom of this fraction times x plus 4. So that's going to be a negative 3 times x plus 4 all over x plus 4, and we want that to be greater than 0. So writing it over the same denominator as a singular rational expression, I'll have x minus 3 minus 3x minus 12. And that's going to be greater than 0. We'll collect our like terms, and then we'll be pretty close to working on this. That's a negative 2x, and then minus 15, all over x plus 4. So I've reached my first objective, and that is to rewrite this thing as a single rational expression with one side equal to 0. Now, when we do our interval line test on rational expressions, it's a little bit different because not only do we include the zeros of the function, we also have to include the x-intercept. So what I want to do is I want to graph the zeros of the function. So I'm going to set this negative 2x minus 15 equal to 0. And what's the value of x that will make it equal to 15? That's when negative 2x equals 15, or x is a negative 15 halves, which is negative 7.5 or negative 7 halves. So I know I have a negative 7 halves or negative 15 halves, so 17.5. Either way, it's not going to make that much difference. It's a nice terminating decimal. And the other one is when x is a negative 4. So here at a negative 4, I have a vertical asymptote. So we want to graph both the vertical asymptotes and the zeros of the function so that we get the intervals on our number line. So really what we've done is we've broken it up into 1, 2, 3 intervals on our number line. We want to use our interval line test to see what kind of values we'll get in each of these intervals. So the first interval I'll try out here, a number like negative 8. If I plug in a negative 8, negative 8 times negative 2 is a positive 16 minus 15. That'll be a positive. And then a negative 8 minus 4, that's going to be a negative. So negative divided, or positive divided by negative is negative. So in interval 1, it's going to be negative. For interval number 2, I want to try a number somewhere between 7.5 and a negative 4, so I'll just do a negative 6, negative 7, something like that should work. So negative 6 times a negative 2 is a positive 12 minus 15. That's going to be a negative number. And negative 6 minus 4, that's a negative number, so it's negative divided by negative, which will end up being positive. So in interval 2, it'll be a positive value. And then finally, in our last interval, interval 3, we try a number bigger than negative 4. I like 0. So it's a negative 15 over a positive 4. It's definitely a negative number. Since our inequality sign says we want only those values that are greater than 0, I know I'm in interval 2, and writing in interval notation, we have a solution set that is negative 7.5 or negative 15 halves. You know, we normally talk about leaving it as fractions if possible, and going up to a negative 4. Neither one included because we want it to be greater than 0. And negative 7/5 or negative 15 halves would be 0. We don't want to include that. And the negative 4 is undefined, so we can't include it. So that is our solution set for D.